Good evening, everyone. Welcome to DSC cohort of Floxus DSC cohort, the third day here. So, unfortunately, yesterday, due to some technical issues from YouTube, our live stream got interrupted, and we were discussing master theorem that time. So, I'll be starting from where the stream was cut off, and we will continue after that. Okay. So, yesterday we were discussing about master theorem. Okay, so yesterday we were discussing about master theorem and the stream got cut off, so we will start from there itself. So as I was discussing, uh, what was master theorem is, what was master theorem was sometimes we get recurrence relations during analysis of our algorithms, and solving recurrence and computing the time complexity from uh, time complexity of the algorithms by when we have some recurrence relation. Suppose we have a recurrence relation like this. We have a recurrence relation like this. And so if I'm getting a recurrence relation like this, so what is the time complexity? What is the big O of function? What function should we write here? This becomes a grave issue because we do not know about it. We do not know about it. So master theorems comes into play here, just right here. Okay. So what is master theorem is? Master theorem suggests that there are three steps involved in master theorem. First one is the identification. Identification that the recurrence relation can be solved using master theorem. Not all recurrence relations can be solved using master theorem. That is the case. So first one, yes, Rodlana, we are discussing master theorem itself. So first step is the identification that the problem, the recurrence relation in hand, is solvable by master theorem. And how do we identify this? Any recurrence relation to be solvable using master theorem will have this structure, this form. The t function will look like this. Tn is a t n by b plus some function. Plus some function, and there are some criteria involved here. What criteria are there? Okay, as I was discussing yesterday, this function, inner t function, will always be a fraction. This inner t function will always be a fraction with input space as the numerator, and the denominator will be some number. Denominator will be some integer, and thus we get a condition as the b should always be greater than 1, so that we are getting numbers in this form: n by 2, n by 3, n by 4, and so on. If it is n, then it is not master theorem solvable, because b should always be greater than 1, and this is one of the key identification of the recurrence relation that are solvable by master theorem, that the inner t will always be a fraction. Inner t will always be a fraction. Again, we also have one more. We have one more constant here named a, and this a has the liberty that it can be greater than 1 and also equal to 1, because not so that we all these equations, like say tn equals to t of n by 2 plus say cn, this is solvable by master theorem. Why? Because b here is 2 and a here is 1. A here is 1, b here is 2. This condition is satisfied, this condition is satisfied, fn is there as cn, so this is solvable by master theorem. Similarly, if we proceed with another say one more recurrence relation, we have as tn equals to 3t n by 4 plus say n by 2 into c. Again, This one is also solvable by master theorem, because the b here is greater than 1 and the a here is greater than equal to 1. So both the conditions are satisfied. We have a function that is equals to n by 2 of c, and thus this theorem is, this reconciliation is also solvable by master theorem. Now let us consider one more example here. Suppose the reconciliation looks something like this: 4t n log n plus n by 2 c. Now here a is greater than equal to 1, but this down here, the b is not not greater than 1. Hence this equation out here is not solvable by master theorem. That is a catch here. So first thing, the first step involved while we have any reconciliation in hand is, can we solve it using master theorem? So the first thing involved is the identification of the reconciliation using two criteria. The a should be greater than equal to 1 and the b should be greater than 1. This is the only thing that we have to check here, nothing else. The second step involved here is, okay, let me just erase this part. I will write here only. Okay, so the first step was to identify the problem. It is solvable by master theorem. For identification, we look over only two things: a, b, and the function at the end. A should be greater than 1, b should be a should be greater than equal to 1, b should be greater than 1, and there should be a function. Second step is we calculate the value of a variable named d. Suppose we call it d. And what is d? D is the log of b base a. We can compute this value d, which is log b base a. In our case, the equation was something like this: t, suppose it is 2 t n by 4 n by 2 plus, suppose it is 1. Okay, suppose it's like this. This is master theorem solvable, we all know. Okay, suppose this is O. This is master theorem solvable as this is greater than equal to 1, this is greater than 1, a and b both satisfy. So we now calculate d. What is d? D is log b base a. This is log 2 base 2. This comes out to be 1. Okay, any doubt till here? Any doubts? Okay, so we now proceed further. After we have the value of d, what we do is we note down the value of another variable that we call c, and c is nothing. C is nothing. C we already have. And what is c? C is, we will look at this function, this end function out here. What is the end function out here? For c, we will be looking at our initial recurrence relation. Suppose the initial recurrence relation is something like this: k t of n by b plus, we have a function here. So we will look at this function for our c. And what is this function? We will look whether the function, what is the complexity of this function, what is the O of this function, and we will note down it as it in a form of a polynomial. How? If it is 1, we all know that if it is 1, we can write this as n to the power 0. Okay, in other cases it will already be given n power 3, n power 4, n power 5, anything in such forms. Okay, so we note down this c. We have this function at the end of our recurrence relation as an addendum. We note down what is the big O complexity of this function, and we note down it as n power c, and we get our c from here. The fourth step involved is, we have our d from log b base a, and we have our c from and 3 power c from here, from the function. Now, if we have this c and we have this d, what we do is we look at the relation between these two. What is the relation? The relations are this c can be less than d, this c can be equals to d, this c can be greater than d. Only these three conditions can prevail. And if these three conditions prevail, we have our answer. As if the c is less than d, then the final time complexity comes out to be theta of n power d. Theta of n power d. If the c, the function's polynomial value, exponent, and log b base a both are equal, then the final time complexity comes out to be O of n power c, this is the original function as the addendum, into log of n. And the third part, if the function's exponent, addendum's exponent, is greater than log b base a, then the time complexity comes out to be theta of fn. Some places this theta is also mentioned as big O. Don't confuse theta and O. They both are asymptotic notations. Big O represents the worst case scenario. Theta is the average case. So you can consider both of them here. Okay. I think this might be clear. So what we have to do, we have to just look at 3 steps. First, when we have any recurrence relation in our hand, we identify whether this recurrence relation is solvable using our master theorem or not. For this, we look at 2 variables. First one is the number, the integer that is multiplied with the inner t, and the fractional part, the denominator of the fraction. This, and we denote this as a, this as b. Now what we do is we compute d. And what is d? D is computed as log b base a, the denominator of the fraction, based with the number that was multiplied with the inner t. Then after we have the d, we look at c. And what is c? C is the polynomial's exponent that is out here with the functions that is added to the recurrence relation. Now what we do is, when we have c and when we have d with us, then we look at the relation of c with the d, and only 3 conditions can prevail. C can be less than d, c can be equal to d, and c can be greater than d. And if c is less than d, the final complexity comes out to be big O or theta of n power d. If c and d both are equal to each other, then the final time complexity is theta of n power c into log n. If c is greater than d, then final complexity comes out to be theta of function of n. I think this should be clear. Any doubts still here? I don't get the third part. Agenda today's session concluded that by cash once again. No sir, please start again. Okay, once again, sir, I don't repeat. When we use finding complexity of recurrence. Yes, Siharsh. We use master theorem while finding the complexity of recurrence relations, and when the recurrence relations are master theorem solvable using the criteria A and B. Okay, so we proceed. Now we look at one example one example of a recurrence relation that is master theorem solvable. Okay, suppose we have a recurrence relation that looks like this. By the way, for your information, this recurrence relation is of a merge sort algorithm that we will study later in this course. Okay, this recurrence relation comes out to be of a merge sort algorithm. Okay, and how it comes out to be, we will. Okay, is it clear now? Ayush says my voice is not clear. Okay, is it clear now? Okay, I am proceeding. So we have this recurrence relation out here. Okay, now first step was to identify whether this recurrence relation is solvable using master theorem or not. So for which we look at two things, A and B. The A here is 2 from this thing. Okay, let me use different colors for A and B. Okay, so the A is 2 and B also is 2, and both satisfy the condition was because this must be greater than equal to 1, this must be greater than 1, and both are satisfied. So and the third one is we should have a function out here as addendum, and we have a function out here. The function is theta of n. So all the three conditions are satisfied. So we have identified that the following recurrence relation can be solved using master theorem. Now we proceed with the second step. What was the second step? The second step was calculation of d as log b base a. Now what we do is we calculate our d. Second step was calculate d as log b base a. Now what is our d here? The d here is log b is 2, base is also 2, and it comes out to be 1. Our d is 1. Now what was the third step? Third step was identification of c. Third step was what is c, and what is c? The c is the function. So we get the third step here. What was the third step? To get c. And what is c? We have a function that looks like this. Okay, and we know the c. How can we get c from here? For getting c, we will look at the function, and c lies here. Okay, so we can write this function as O of n power 1. And so we now understand that our c out here is 1. Okay, now we have our c and we have our d. Now what was the next condition? Next condition was nothing. Next condition was to get the answer by looking at what is the relation between c and d. In our case, the relation comes out to be that both are equal. Our c is also 1 and d is also 1. Okay, let me write it like this. It will be more clear. Okay, in our case, the c is equal to d equals to 1, and this is nothing but the second condition of master theorem, that if c equals d, and if c equals d, then the final complexity comes out to be theta of n power c log n. So we can write down our answer as the final complexity will be theta of n power c into log of n. And what is c out here? In our case, it is n power 1 into log n, which comes out to be theta of n log n. Theta of n log n. So we can fairly say that this recurrence relation out here, which is by far the recurrence relation of a merge sort algorithm, has a complexity that is equals to n log n. Any doubts still here? Okay, I think everybody understood master theorem and how it is useful. Should we move on to another example, or should we proceed with the next topic? Okay, how we got c again? C. Okay, I will repeat just for who is there? Gaurav. For Gaurav says, how did we get c? C, Gaurav. Every recurrence relation will have this form. Every not the recurrence relations that are solvable by master theorem will always have this form, this function. Okay, this will be the, okay, I think this might not be that much clear. Let me just erase it. Okay, 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 1 minute, just give me 1 second. So every recurrence relation that can be solved using master theorem will have this form. I think this will be clear. And the last thing will be a function. Okay, and this function will be in the form of a complexity, be it theta or be it O, big O of something. Okay, and if this is a big O or theta of something, this can be in this form: big O of 1, big O of n square, big O of n cube, and so on. Okay, now this one can be written as big O of n part 0. This is what is n part c. This is from where we get a c, the exponent of this polynomial. I think this is clear now. Okay, Gaurav. Yes, you are right, Gaurav. So we now proceed with the next topic. Okay, just one more thing. As I just told here that this recurrence relation is of a must-sort algorithm. Now, one thing is there: how do we get the recurrence relations out from any algorithm out there? We know we can get n square, n cube, O of 1 from our last 2 classes. We know how to get those complexities out from any algorithm or pseudocode. Now, if we have, how do we get recurrence relations out from any code? Okay, so for that, let us see this example. Suppose we have an algorithm like this, and just keep in mind, recurrence relations will always come into picture when we are dealing with recursions. From the same word, recursion, recurrence. Just remember this. Suppose we have a function something like this, which takes in a value n, does something on it. Suppose it has a loop inside it for int I equals to 0, I less than n, I plus plus, and it computes something like this in O of 1. Here, the inner complexity is O of 1. So if I tell you what is the time complexity of this function, so what we will do, we will go inside out. As I have already mentioned, the complexity of the inner will be O of 1, or you can always find what is there. The complexity of this thing will be O of 1 for the loop, and the function is called 1 times, then it is O of n. If it is called 2 times, it will be 2 into O of n. If it is called 3 times, then it will be O of 3 into O of n. These things, yes, all recursive problems have these relations, Saharsh. Now, suppose what we have here is, I'm calling this function as this, func of n by 2, then again func n by 2. I'm calling this function 2 times. I'm calling this function 2 times. So we already know, if I'm calling it 2 times, for 1 time, this function has a complexity of O of n. For 2 times, it will have O of 2 into O of n. But now, what is here? I'm not calling the entire space n. I'm only calling the space n by 2. So the complexity of the outside function, main function, okay, will come out to be 2 times the time complexity of n by 2. Why 2 times? Because first time I'm calling it here, second time I'm calling it here, plus this is the complexity, plus this function out here has an internal complexity. This is the calling complexity. For calling this function 1 time, I have to call it for O of n by 2 or t of n by 2, suppose. For calling it second time, I have to adhere to the complexity t of n by 2 again. So we come down to 2tn by 2 that I have written here. Again, each of these function calls has an inherent complexity of O of n. So this O of n must be multiplied here, must be added here. So the final complexity that we get here is t of n is 2t n by 2 plus O of n. Okay, and this is what is A, this is what is B, this is what is f of n, which is having a C which is equals to 1, and thus this is also solvable by master theorem. This is how we get recurrence relations out from any recursive call. Any doubts still here? Okay, repeat how to find relation once again. See, any recursive function, what will be there? What are the components of a recursive function? There is a recursive function. We have a definition of recursive function out here. Then what we do? We make a call to this recursive function. Recursive function. Okay, and why we call it as a recursive function? Because this function calls itself inside it with a decreased search space. Okay, this is what is a recursive function, a function that calls itself from inside itself. So we have a recursive function, we make a call to the recursive function. Each call to a recursive function has a complexity of it. What is a complexity? The complexity will be the execution complexity of one block of this recursive function. Let's call this takes O of n time. Okay, now for same function we have a constant complexity of O of n plus if it is a recursive function, we are also making another call to the same function. So this will be O of n by 2. Okay, let me repeat myself a bit clearly. I think this is getting a bit confusing for you. Suppose I have a function. It performs some operations. Suppose these operations take O of n time. Okay, and inside this same function, it again calls itself by reducing its search space. This is what a recursive function is. It calls itself. Now what we have to find? We have to find the complexity of the entire function. Now to find the complexity of the entire function, what we are encountering here? For solving this function, we always have to encounter this O and this complexity we have to adhere to, that is O of n. And again we are making the call to the same function. So what will be the complexity of this? This complexity is nothing but this complexity, T of n. But in this case, this T of n is T of n by 2. Okay, so what happens? What happens is, again, for this Tn by 2, when we enter, we have a O(n) plus, again, we have a function call that calls n by 2 of it. So this is T of n by 4 out here, and this goes on. Okay, this is how we get recurrence relations from our recursive functions. Okay, so in our example that I was giving, what we had is, we had a function, we had some set of lines, say they get executed in O of n. Suppose there is a loop, int I is less than n I plus plus, and it inside it has some set of lines that gets executed in O of 1. Okay, again inside this function I am calling this function again recursively by reducing the subspace by n by 2, and again calling the same function by reducing the subspace by n by 2, and this is the entire definition of the function. Okay, now what we have is, what is the complexity of the entire function? Okay, so what we do while calling this function, whenever a call is made to execute till here, the complexity is O of n. Okay, and to execute this is again a call to the same function. So if the complexity is T of n here, the complexity of this will be T of n by 2. and then this complexity of this will be T of n by 2. This is what we write as the complexity, overall complexity T of n will be equals to 2 T n by 2 plus O of n. O of n is the constant complexity that we execute every time where is the complexity that is the constant complexity that is executed every time a recursive call is made. And this Tn by 2 is the complexity of the recursive call. This Tn by 2 is the recursive call. Okay, I think this is clear now. How are we getting the recursive recurrence relations out from a recursive calls? Any doubt till here? Okay, so the time complexity, symptotic notations, and everything is finished. If in case of any doubt, you can just look forward to the previous two videos. They are there in the YouTube. Now, the last videos, last topic was must sort itself, but due to some technical reasons, we could not finish. It could not go live. So I think that part is clear here. Okay, so now we move on to the next topic. Today's agenda is mathematics. Mathematics, or in simple terms, number theory. What is mathematics or number theory is while dealing with some problems in data structures and algorithms or CP in general. Okay, we come across some simple concepts. Okay, some simple concepts, but which require major focus here. Why? Because suppose I tell you to find suppose, okay, let's take one example that we are going to deal here. I ask you find factorial, find the value of 5 factorial. What will you do? You will do something like this, and you will come out with an answer that is 120. Now, this is something everybody can do. This is something everybody can do. Okay. Now, if I ask you, tell me the number of zeros which are, in 5 factorial, trailing number of zeros. What is trailing number of zeros? The number of zeros from end till here. Number of zeros before any other number is encountered from the right side. So in 5 factorial, the trailing number of zeros is 1. Okay. Similarly, sir, what is the use of master theorem? Where we will use this master theorem in programming of any language? See, we do not use time complexity or master theorem in general while programming in any language. Okay, where master theorem or time complexity comes into picture is while designing suppose you are dealing with a question. Okay, now what happens is okay, I will proceed with this topic later after finishing this small discussion over why is time complexity necessary, as Funny Tom is asking. See, what happens is if you will go into any competitive programming website, okay, like Hacker Rank, Earth, Code Forces. Okay, I will explain this complexity too. Okay, Code Forces, etc. Whenever you get any question, you get 2-3 things along with it. Okay, one is the problem statement. This we get a story and you have to solve this. Okay, suppose I am telling you I will give you an array. Of n numbers, and you have to give me number of prime numbers in this n arrays. Suppose I give you 1, 2, 3, 4, 5. You have to tell me that 2, 3, and 5 are the prime numbers, and the output will be 3. This is the question. So in any competitive programming or questions asked by the companies, only problem statement is not given. One more thing is given: range of values of n. Range of values of n. They will tell you that the n lies between this and this. The n lies between some lower value and some upper value. And why is this range important? This range is important because while dealing with complexities or while dealing with algorithms, as we have already seen, for different input values, the algorithms behave differently. Okay, and that is why this range is important. So competitive programming websites or any problems will be supplied with a range of the input values, also with the size of the input values, and this is what we have to undertake. This is what we have to look carefully to. Okay, now suppose one more thing to keep in mind is all model computers, your code will be executed on servers of HackerRank, okay, something like that, and all servers are till date are capable of executing this many. I think it is 10 to the power 6 or 10 to the power 8, something of this sort. Okay, operations per second. I think this is 10 to the power 8 only. 10 to the power 8 operations per second. Okay, so your code should only execute 10 to the power 8 operations or less than 10 to the power 8 operations per second. Then only your code will be accepted by those platforms. Otherwise, you will get an error named TLE, time limit exceeded. What this error tells you is that your program was good. We don't know whether your algorithm is correct or not, but the test cases that we have, the input ranges that we have, your program was trying to execute more than 10 to the power, was trying to solve more than 10 to the power 8 operations per second, which our servers cannot handle, and thus we are throwing a TLEX error. So as a coder, what should you do is you should always try to limit your algo such that it never executes more than 10 to the power 8 operations per second. Okay, and that is why we find that is why we all, whenever we code an algo, whenever we write the pseudo code or we write the code of an algo, we try to get the time complexity of this algo. If we have the time complexity of our algo in, say, it is n to the power 4, I am using four loops, and the complexity comes out to be n to the power 4. Now what I have to see is whether with the given range of n, suppose the range of n is given like something like this, n lies between something 10 to the power 6. This is given in the question, and I have designed an algo that has 4 loops, one loop inside another loop, again another loop inside this loop, and again another loop inside this loop. This is my algo. Okay, and the complexity comes out to be O of n by n of 4, n power 4. This is easy to find from this algo. The complexity is O of n power 4. The question out here is, if I submit this solution which has a complexity big O of n power 4, whether we will get AC accepted or whether we will get TLE, time limit exceeded. Okay, so how to find it? We will look at the range of n given in the problem. We have a range that is 1, n is greater than 1 and is less than 10 to the power 6. So what we look here is always considering the worst case. And what is the worst case? That any one test case is there where the value of n is in the range of 10 to the power 6, and if this test case is applied to our algorithm, so our algorithm will do this much operations, 10 power 6, because the test case is n and our complexity is n power 4. So our algorithm will try to evaluate this many operations in 1 second, which comes out to be 10 power 24. Now any server out there can execute only 10 to the power 8 operations per second, and we are supplying it 10 to the power 24. We are telling it to compute 10 to the power 24 operations per second. So the server will fail and we will get a TLE, time limit exceeded. So what is this? We should this is an red flag. TLE is a red flag that our solution, which is a O and Part 4 solution, is not the correct solution. What we have to do is, even though it is giving the right answer, what we have to do is we have to minimize the complexity. A better complexity of n square, n cube, n, or n cube log n, anything which is better than n power 4. Given that this complexity satisfies the worst case range. What is the worst case range? 10 to the power 6. Any complexity that we are thinking out here should satisfy this worst case range, and the final number of operations should not exceed 10 to the power 8. And if we are capable of doing that, then only we will get a AC in all the test cases, and our solution will get accepted. Okay, that is why we should always strive for less than 10 to the power 8 operations per second. And that is why whenever we are designing any algorithm for any solution, any problem statement that we have, we design an algo. The first thing that we should do is design this algo on paper. Okay, on paper or in mind, whichever way you find it quicker. Second thing should be to find the complexity of it. Why complexity? Because the input will have a range, okay, and AC is accepted. TLE is for time limit exceeded, AC is for accepted, WA is for wrong answer. Okay, this n will always have a range. We will look at the highest range, okay, and whichever complexity that we are getting out here, suppose we are getting log n. So what we will do is we will put log n and we will put the highest range of n, highest n possible. And if this comes out to be less than 10, and we should strive that this should always be less than 10 to the power 8, then only our solution will get an AC, that is accepted on the online judges. Okay, how to deal with test cases and coding challenges, we will come out to that. Whenever we are solving any question, I will tell you. Okay, so this, then only we will get an accepted. If by far, if you are started, if you're following this logic that we are getting a problem statement, I'll design an algo, I know the coding, C++, Java, Python, I'll directly code it, submit the solution, you will always get a TLE. I am not saying that you will always get a TLE, but chances are great that you will always get a TLE because you have not computed the complexity of it. And if you have not computed the complexity of it, you do not know whether your code is executing more than 10 to the power 8 operations per second, or less than 8 or more than 8. If less than 8 or equal to it, then it is good. But if it is computing more than 10 to the power 8, it is not a correct solution. It is not a correct solution. So what we should always do is, whenever we are getting any problem, first write the algo on paper, compute the complexity. If it is, then look into the highest range of n, calculate the number of operations that your this algo will solve. If it is more than 10 to the power 8, if it is more than 10 to the power 8, discard this algo, try to optimize it further, then again the same process. And to find this complexity, if you are using any recursive calls, then you will get a recurrence relation. And if you are getting a recurrence relation, you will have to find the complexity using master theorem. That is why we are learning master theorem. That is why master theorem is important. Okay, so whose doubt was this? Okay, Funny Tom, I think I have answered your question. What is the use of master theorem and when we will use it in a programming of any language? So we do not directly code master theorem or anything of that sort. These are all pre-processing steps. Before coding the solution, we compute the complexity, and while computing the complexity, we strive for a complexity that will get us number of operations less than 10 to the power 8 operations per second. And if we are capable of achieving this complexity, then we will try to code that solution on the online judge and submit it. And if we have done this pre-processing, so you can be sure that your solution will always get accepted. At least TLE will not come. Okay, you can get wrong answer if you have missed any test cases, but you will never get a TLE if you are adhering to time complexity. That is why time complexity is important. That is why master theorem is important if you are dealing with recurrence relations. Okay, I think I have answered the question. So, acha, one more thing. Let me just tell you one simple logic. One simple logic. How should we know which what is the complexity that we should strive for? Okay, while designing, suppose you have designed the algorithm. Okay, now what I told you, after designing the algorithm you should compute the complexity. After computing the complexity you should look for the highest range of n, put that highest range of n in your complexity, and then find out whether it is greater than 10 to the power 8 or 10 to the power, less than 10 to the power 8. A simple solution to this is, if you are not willing to do all this, what you can do is just look over here. If the range of n is given something like this, okay, let me just tell. Okay, if the range of, okay, if the range of n is something like this, 10 to the power 8, and you already know that 10 to the power 8 is the highest number of operations that we can solve. So what should we strive for? We should strive key our solution is O of 1 or O of n, O of log n. If it is O of n, then also we will be executing only 10 to the power 8 operations per second. It is by far, we are touching the highest limit of the servers, but this is good. If we are dealing with O of n, if our algorithm has a complexity of 1, then it is good. We are only executing one command per one operation per second. Log of n, then also it is good, because we are dealing with something as log of 10 power 8, which is by far less than 10 to the power 8. Now, if our n is given in, say, some range, suppose something like this. What is this?